there are some situations where it is necessary to deal with overcounting. How do we correct for overcounting? Consider this example. Suppose that we have two white pawns and one black pawn. And the white pawns are not distinguishable one from the other. We want to figure out how many arrangements are there, how many ways to place them in order, 1, 2, 3. So you can, of course, list out the orders based on where the black pawn is located. So the possibilities for the black pawn are, first possibility, the black pawn is last. So it's white, white, black. Second possibility, the black pawn is middle, white, black, white. And last possibility is the black pawn is first, black, white, white. So there should be 3 arrangements. All this is wonderful, but here you have a few possibilities and it's easy to list them out or to count them directly. How can we figure out how to deal with this in general? So I can always imagine, metaphysically that seems to be clear, that objects are distinguishable. I can imagine that the white pawns they have a number etched on them. Maybe the number on the first white pawn is 1, and then the number is 2, and the black pawn it has an etching of the number 3. Maybe an etching that I do not see, but I believe nonetheless exists somewhere on the pawn, maybe at its bottom. So if I place the 3 objects, which I now consider distinct in linear order, that is first, second, third position, there are altogether 3 factorial possibilities. So that would be 3 factorial forms. Right? If I were to fill a form for each possible arrangement, I just have to count the number of papers. It's 3 factorial papers, which is 6 papers. On each paper there is a 3-digit code. Now, because I cannot distinguish the 2 white pawns, several codes will correspond to the very same outcome. So for example, if I see the code 1, 2, and 3, I know that white pawn is first, white pawn is second, and a black pawn is last. But if I also see the code 2, 1, 3, it's a different code, and yet it encodes the same observable outcome. White pawn first, white pawn second, black pawn last. Notice that there are only 2 documents in this situation, because I can only not distinguish between the white pawns. So those 2 documents are corresponding to the same information, to the same outcome. Similarly, if I see that the black pawn is in the middle, the code is 1, 3, 2 or 2, 3, 1. Both of those documents represent the same outcome. And if the black pawn is first, again, both of those documents represent the same outcome. So that means we have more codes than we have outcomes. But what's wonderful in this particular arrangement is that there are exactly 2 different codes for one outcome. 2 different codes correspond to one outcome, 2 different other codes correspond to another distinct outcome. So what you can imagine doing is you group those papers based on the outcomes they represent, and you staple them together, placing perhaps as the top paper where the numbers 1 and 2 are in order. So 1 and 2 here, this would be the top paper, this would be the top paper. So there are 3 piles, and in each pile there are 3 papers. Right? So let's see what we observe algebraically. So we have 3 piles, and in each pile there are 2 papers. Now the piles correspond to the distinct outcomes. No longer the papers, but the pile, the staple document corresponds to a different paper. And notice that this will equal to 3 factorial. Now, the piles is our number. So what I see is that 3 is equal to 3 factorial divided by 2 in this particular case. Right? So that means what? That means that if I have a very nice kind of overcounting, that means each particular event has the same number of codes. So for example, if I had, here I had, let's say, k files, each with each file having j documents, and if I know that k times j equals to some number n, then k, basically that means that what? That means each file corresponds to a unique outcome. And this unique outcome is repeated across j codes for a total of n pieces of paper. So I can compensate for overcounting. In other words, I have more codes than outcomes by taking the number of papers and dividing by the number of repeating codes. Right? That means that gives me the number of piles, which now represents in one-to-one correspondence the number of distinct outcomes. So let's try a slightly more complicated question. So now we have 6 pawns, and any 2 pawns that look alike are indistinguishable. So we have 2 white pawns, we have 3 black pawns, and we have a zombie pawn with a black head and white body. How many distinguishable linear orderings are possible? Well, again, I can imagine that every object is distinguishable. Perhaps there is an etching at the bottom of the pawn. So this pawn has a number 1, 2, 3, 4, 5, and 6. So if I just look at those numbers, any ordering of distinguishable 6 objects, that would be the total number of codes. So we have whatever comes first, second, third, fourth, fifth, and sixth. That's my form. So total number of codes clearly is 6 factorial. How many codes per outcome? Notice that I am free to rearrange 1 and 2 in any ordering. If this is the ordering I see, I can always switch 1 and 2. And I can always switch any of the 3 black pawns wherever they are located. So how many repeated codes are possible? So how many times is the code 1, 2, 3, 4, 5, 6? How many ways can it be changed and still indicate the pattern observed on the board? Well, think about it. For this code, I have 2 interchanges here, and independently 3 factorial interchanges here. So the total repetition of each code will be 2 factorial times 3 factorial. You can include 1 factorial if you like. So this means what? This means that if I print every code, I will have 6 factorial documents. And a bunch of those documents are actually talking about the same exact situation. How many? For each particular outcome. For example, if this was the observed outcome, I see 2 white pawns followed by a hybrid pawn followed by 3 black pawns. If that's the outcome that I see, I will have 2 rearrangements here. So the code that reads 1, 2 will be indicating the same as if it begins reading 2 and 1. So any interchange of 1 and 2 mean the same thing. Any interchange between 4, 5, and 6 means the same thing. That means that we can group those documents based on the outcomes they encode, and each outcome will be then represented by a column. Can you imagine that? So you have one column of a bunch of codes, they represent one outcome. So for example, maybe one column representing this outcome. Another column will represent another outcome. Another will represent another outcome. The stacks of paper in each column are of the same height. That's very important. Each stack is exactly as high as the other. That means that I overcounted every actual outcome by exactly the same amount. And that amount is 2 factorial times 3 factorial. In other words, in this situation, in this experiment, each pile will be 12 papers deep. So there will be a bunch of them, and then 6 factorial divided by the depth of the pile, it tells us how many piles. And now there is a one-to-one correspondence between the pile and the outcome. Hopefully that is clear. So next, let's consider a question that I personally find nearly impossible. I'm terrible at spelling, and the word necessary, I can never remember how that one is written. I had to, again, look through my phone to make sure I spelled it right. So suppose that we want to consider all rearrangements of the word necessary. So that means I have one N, I have 2 copies of E, I have 1 copy of C, I have 2 copies of S, I have 1 copy of A, 1 copy of R, and 1 copy of the letter Y. Now, you can see that, of course, here I labeled the letters. I imagine giving the numbers like this. So 1 is for N, 2 and 3 are for the 2 E's, then 4 is for C, then 5 and 6 are for S, 7 is for A, 8 is for R, and 9 is for Y. So now instead of poles, I am moving around letters. So I have, these are the type of poles that I have, different objects among which in each category I can distinguish between them. I cannot tell apart the E's, I cannot tell apart the S. So again, very similar situation. I see that I have 9 letters. If I regard all the letters as distinguishable for a moment, I have 9 factorial arrangements of those letters. One of them is necessary. And what happens now? We can see that that some of those codes are encoding the same outcome. So what would be the same outcome? Well, so if I look at the ends, well, the ends don't contribute anything. So there is 1 factorial for the ends. Or in other words, I can change the E's, so that would be 2 factorial. There is a 1 factorial for C. There are 2 factorial for S. And the rest are also 1 factorial. So the 1 factorials don't contribute anything really. I just have 9 factorial divided by 2 factorial times 2 factorial. Here is another example. So you have 10 competitors, 4 Russian, 3 US, 2 Britain, 1 Brazil. And imagine that when they finish their Olympic tournament, the names are not listed, only on the billboard you see the nationalities. So for example, suppose that you see this string. So that means that first winner was Russian, second was US, third was US, fourth was Russian, fifth was Brazilian, sixth was again US, 7 was Russian, 8 was Russian, and then we have 2 British came last. So that's a ranking. So you can see here, we cannot distinguish the R's among themselves, we cannot distinguish the U's among themselves, and etc. So what I imagine is that if I could see their names, I have a total of 10 factorial rankings of the individuals on first name basis. But that's overcounting. Because again, I can, in this situation, I can interchange any 2 R's. I can interchange any 2 U's, etc. So for every particular ranking, if this was a ranking I received, how many interchanges are possible. So you can see that there are 4 factorial permutations for the Russians among themselves. There are 3 factorial independent permutations for US players. There are 2 factorial permutations for the British and 1 factorial permutation for the Brazilians. So this would have, of course, 10 factorial is a pretty large number, but what you can imagine is that I can print out the individual names and then bring the listings into one pile that correspond to an undistinguishable ranking by nationality. So what is the denominator? Again, it counts how many documents I have in my pile, in each pile. The important thing is that for every distinct ranking, there are exactly the same number of documents. In other words, the pile is always at the same height for every different distinguishable outcome. And so what I do is I identify the pile in a one-to-one correspondence with the outcome. And what is this counting? The 10 factorial divided by the number of documents in each pile gives you the number of piles, and therefore the number of distinguishable outcomes. So in general, if we have n objects, and one of which are alike, and two of which are alike, etc. Where I see that n1 plus n2 plus, let's say the last one is nr equals to n, then the number of distinguishable linear orderings is equal to n factorial divided by n1 factorial and 2 factorial all the way till nr factorial. So this deals with a special situation where overcounting of each individual outcome is the same for any other individual outcome by the same number.